Okay, welcome back to this session after lunch. I hope you had a good lunch break. We're now continuing with the second block of the session with how to collect data. So, and with much further ado, we'd like to hand over to Amanda for the first presentation of the session. Amanda, are you with us?
I am with you. Thank you. I'm going to go ahead and share my screen now. So as mentioned, my name is Amanda Porter. I'm an associate professor at the Vrije Universiteit in the Kin Center for Digital Innovation. And today I'm presenting on some research that I've been working on for the last couple of years with some colleagues of mine, also in the Kin Center, Philip Churcher and Marlene Hausman. And in particular, my research has been looking at how different digital technologies can help us to tackle grand societal challenges. So the project that I want to share with you today is called Save Our Oceans. And this is a multi-sector partnership in the maritime industry in the Netherlands. And it was established in 2014. And it was established to specifically tackle the Sustainable Development Goal number 14, life below water. And essentially, they had a couple of aims in creating this partnership. On the one hand, they wanted to develop some sustainable innovations. So innovations that would protect the ocean and also harness the ocean resources sustainably. But they also had kind of a more long-term goal, and this was to actually make the maritime industry more sustainable. So the vehicle that they actually used to try to reach these goals was through innovation challenges using a digital tool called crowdsourcing. So crowdsourcing is a little bit different than the other data collection tools that I think will be presented in this session. Instead of collecting information directly from the ocean, what crowdsourcing does is it collects experiences, ideas, knowledge, and solutions from people, and usually a very wide range of types of people. So if an organization wants to use crowdsourcing, essentially what they're doing is they are broadcasting a problem that they would like to have solved through an open call online. And in the case of Save Our Oceans, this platform was completely open. So anyone could submit an idea or make feedback on an idea. So maybe you're wondering why crowdsourcing? So we know that crowdsourcing is a good tool for a number of reasons. First, it allows organizations to engage in distance search. So by this, looking for knowledge, ideas, and experiences outside of the organization, even outside the industry. So by doing this, you're able to increase both the number of potential solvers that you're working with, but also a much more diverse range of solvers from very different backgrounds, from industry to university students, and also small companies. And what we know is that crowds tend to really do well when it comes to creativity. So they are able to have outside the box ideas, which is an advantage because sometimes when we're an industry expert, we may tend to have some blinders on because of the knowledge that we have of our industry. So crowdsourcing is really good for tapping into this creativity. And there's a number of ways that crowdsourcing can be used. And probably the most typical way is to treat it sort of like an online suggestion box, where an idea holder simply submits their idea, but the other idea holders can't read the idea, and people normally cannot give feedback on the idea. But Save Our Oceans opted for a different approach. They used a collaborative crowdsourcing platform, which is one in which when you post an idea, everybody can see this idea. So it's completely transparent. All the ideas can be read by the other idea holders, but also more importantly, people who are in the platform can give feedback on the ideas. And so this is the whole kind of concept behind collaborative crowdsourcing, is that by giving feedback on ideas, interacting, you're able to integrate knowledge from different places, and in doing so, come up with more novel solutions. So one nice example from the Save Our Oceans case was one of the top ideas came from a set of university students who wanted to tackle the problem of plastic waste. So they wanted to create a system of underwater air bubbles that would be used to sort of guide waste in the rivers to the side, to the banks, so it could be collected before it reaches the ocean and becomes part of this sort of problem of plastic soup. And it just so happened that some of the engineers in the Save Our Oceans organizations work with underwater air bubbles for completely different applications for building underwater structures. They were able to come together, combine their ideas and knowledge, and develop this into a prototype for underwater air bubble system that's now being deployed as a pilot in the canals in Amsterdam. So this is just one of the examples of the kind of ways that knowledge is integrated through collaborative crowdsourcing. So the crowdsourcing process has many phases. I listed the phases here so you can see these. For the Save Our Oceans project, the entire process lasted around 9 months. And I don't have time, unfortunately, to talk about all the phases, but one of the key insights from our research was that Save Our Oceans co-created with partners and idea holders throughout all phases of the challenge. And typically, with most crowdsourcing, this co-creation only happens in the second phase, the ideation phase, where the platform is open and used for collaboration. So what I want to do is tell you briefly about how the Save Our Oceans initiative co-created, how they did this in problem formulation, ideation, and then finally focus a little bit on the implementation phase. So the first step in using a crowdsourcing platform is defining the problem. You need to scope a bit, what is it that you're looking for solutions? And this helps to sort of guide and direct the solvers. And in the case of Save Our Oceans, you see here the different problems that they decided to tackle. And what's interesting is when the initiative first started, there was fewer partner organizations. And originally they were interested mostly in this issue of waste management and plastic food. But as they got started talking with more partners inside and outside the industry, they realized that there were other problems that were also salient to these different partner organizations. So they made the choice to actually broaden the set of problems that they would tackle, from the problem of waste management to these 5 problems. And what's interesting about this was what we found in terms of how this impacted the partnership. We found that on the one hand, this helped to increase the commitment of the partners because they together defined the problems, actually sitting together in a day-long workshop. And this was a way to start already sharing and integrating knowledge well before solutions even come in. This was in the problem phase where they could go ahead and share their notions of, hey, what is the big issues that we should be tackling together? And once they got the online platform, which is the second phase for ideation, the organizers actually noticed in the first couple of weeks that they wanted to do something to increase the quantity and quality of the ideas. Because after they talked to some of the engineers who were participating in the platform, they realized actually that maybe this is familiar to this audience, that engineers were a little bit hesitant to post undeveloped ideas on the platform. And in fact, they said, we're used to being correct and talking about feasibility. So how can I share an idea that hasn't been tested? And so this was an interesting point of conversation. What the organizers of Save Our Oceans decided to do was to host a series of offline workshops. They called them brainstorm sessions. And in the picture in the bottom left, you see a brainstorm session that I held with some of my students at our university. And what they did in these sessions is actually teach people how to share knowledge and combine knowledge in the setting of the crowdsourcing challenge. So this was interestingly something that didn't actually come naturally to people, and they had to be taught this. And once they implemented this combination of offline and online, they saw the platform become much, much more successful, much more rich with the level of collaboration, which they were all quite happy with, and involvement with participants from all over the world. And after they sifted through the ideas, they evaluated them, they selected a top 20 ideas that they wanted to work with. And this was also a way in which Save Our Oceans was quite unique from typical crowdsourcing. Oftentimes, crowdsourcing is quite known for being able to develop a lot of good ideas. Many of these ideas don't get implemented. And this was a point of concern for Save Our Oceans. They really wanted actionable solutions. They wanted things that could be developed, clearly making progress. So what they did is they decided to actually co-create with the top 20 idea holders in a series of feedback sessions where idea holders would present the development and the progress of their ideas. And they would actually get feedback from the partner organizations, also resources. So sometimes this involved helping each other create a business plan. Other times it involved showing results of testing a prototype or using some of the partners' facilities to further develop a prototype, etc. So by working together to co-create the solutions, the outcome was actually that they did announce the top ideas, but these were further developed through joint partnerships where they actually partnered with one or many of the organizations in the Save Our Oceans network to continue to work on and implement the ideas. So I want to just conclude with some sort of high-level insights or takeaways from our case, and particularly collaborative crowdsourcing for ocean sustainability. One of the challenges is actually dealing with uncertainty, because when the organizers came to the partner organizations to ask them to join, they could not guarantee anyone an outcome, right? They could not guarantee we will develop an innovation for X, because the whole point of the process was to develop the innovations collaboratively. So this meant they could not guarantee what would happen. But one of the interesting things that this partnership did to sort of cope with this was pooling resources. So they created a model where different partner organizations could make different levels of commitments. So one partner organization could just commit in kind, another partner organization could commit in kind and cash resources, and so on. So by pooling the resources, they're able to reduce a bit this uncertainty that's sort of inherent in this collaborative process. Another key takeaway for using this crowdsourcing platform was how it really lowered the threshold for participation. University students, people within the industry, outside the industry could easily join and get involved. Now, this does also create some challenges in the sense that once you have so many different stakeholders with different interests involved, you have to figure out ways to balance these interests. So, for example, some organizations were really interested in the short term, the innovations themselves. Other organizations were more interested in this long-term perspective. How are we going to make this transformational change? And so some of the mechanisms that the Save Our Oceans did to balance these interests were, for example, in the problem formulation, where they said, okay, let's tackle many problems at once and be quite broad. And that way we were able to be inclusive of people's different interests. But to pull off this challenge, I will say that it was very important to have a committed team of organizers. So this was a group of 5 individuals who were organizing the day-to-day and really monitoring the process very, very carefully to see, for example, in the ideation phase, when the ideas were not at the level they wanted, they jumped in, created these brainstorm workshops. And so in this sense, it's the process itself is quite experimental.
Time.
But one of the takeaways, besides the innovations themselves, was how this process connected everybody in the industry to develop this ocean sustainability network and accelerated this process, a network that was really not that strong before. So if you're interested to learn more, we have some outlets here. We have a short blog that we've posted, very quick read. We have a full paper that we, in the Journal of Management Studies, it's an academic paper, but it's open access. And if you're interested in collaborative crowdsourcing, there's a link to a platform with one of our current collaborators, Innovation Cast. Take a look, and hopefully this presentation will be shared. And well, if anybody's interested in thinking more about crowdsourcing as a tool for their projects, please get in touch with us. We would love to collaborate. Thank you.
Thank you, Amanda. I always really get going when I see methodology issues, so we could discuss that for a long while. There have been a few comments on this online, so we'll ask the audience to post their questions on the Q&A or in the chat during the next sessions. So we'll sum up. So then I'll allow Fredrik to introduce our next talker.
Yes, so next talker, he will be navigating with us without GPS, and that is Roger Berg. Welcome, Roger. The floor is yours.
Yeah, thank you. Yes, hello, I'm Roger Berg. I'm Director of Technology Management at Saab Kockums, which is part of the Saab Group. And Saab is a Swedish defense and security company. And I will talk to you about how to navigate when we don't have a GPS. We at Saab, we work with different technologies, and we also are in the naval business. We make surface ships and submarines and also autonomous systems. So this is a very interesting topic for us. And of course, navigating without GPS, we have done for thousands of years. So it's nothing new. It started many, many years ago, and it's only during the last decade, you could say, or century, that we have used more high advanced technologies. Like we got in the last century, we got different kind of radio navigation systems. And you could say approximately since 3 decades back, we have used satellite navigation. And it is a little bit sloppy to call it GPS-free navigation. The correct term is actually GNSS, Global Navigation Satellite System, because there are several of them today. There are 4 global systems, and they are more or less operational, all of them. We have the Beidou from China, the Galileo from the European Union, the GLONASS from Russia, and of course the GPS, which is the original and the oldest, from the United States. And they have different accuracy, and you can enhance their accuracy with different kind of technologies. The thing is that these satellites are very, very far away. They have an altitude of approximately 20,000 kilometers above the sea level. And that means that the signal that we receive from these are very, very weak. So it's about 100 times further away than we have, for instance, the International Space Station. So what is the problem then? Well, it's quite easy to jam these signals by sending out a disturbance signal. And actually on the left, you can see you can buy these small devices for a couple of bucks that you can disturb your GPS on a car or on a boat and so on. But it's a federal defense in the US to own one of these devices, I could say. And on the right, you see an example of what's happened up in the Arctic area quite easily, where the Russians are doing stuff with the GPS, particularly during military exercises. Then we have something called GPS spoofing, and that is when you send out a fake signal, and then the ship or the airplane thinks that it is in another position. And this is really, really dangerous because you can cause accidents, really, and it could be quite difficult to detect that you are spoofed as well. And on the right, you see an example of also activities that has been ongoing during the last years. Again, the Russians. And then, of course, we have the worst thing, that is when you destroy the satellites. There all the big nations today, they can actually take out satellites with different kind of systems and so on. It's not very popular when you do this kind of exercises because you create a lot of debris up in the satellite orbits, will cause threats to other satellites. And this has been highlighted during the last years now, the problem of the sensitivity of global positioning systems. So actually the US Navy, they are bringing back old navigation techniques to the officers' education. So what can we do then if we have a problem with our GPS? We can, of course, go back to old ways of navigating, but today we have much more advanced technology. We have much more sensors, and we can use combination of sensors to increase our position accuracy. And it's extensive research ongoing worldwide, particularly in the defense sector. And I will give a few examples from ongoing research in Sweden where Saab is involved. The first two examples comes from the WASP program. And for those who have not heard about WASP, WASP is actually the biggest research program ever in Sweden. It's a program focusing on AI, autonomous system, and software. And it started in 2016. And today it's more than 5.5 billion Swedish kronor in total in this program. And currently there are more than 400 PhDs and researchers recruited, and many of these are industrial PhDs from Saab. There are also demonstrators included in this research program, and Saab is a big supporter of this. We support it with unmanned systems and with command and control systems. And the first example is from a guy called Bertil Grälsson at Saab. He worked with vision-based positioning, and that means that he uses a small unmanned surface vehicle you can see on the left there. It's called Piraya. It comes from Saab. And on this one, he uses a 360 camera to take, so to say, a video of the contours of the horizon. And then he combines it with digital satellite data, something called digital elevation models. And on this one, you get, so to say, the altitude of the complete globe. And by combining this altitude data and the image that you have, you can get a picture of the horizon, so to say, and then you fuse it together with the convolutional neural network, and you can get very good positioning. The second example is from Morten Lager, also at Saab. He works with low resolution data. He takes a C-chart where you have very low resolution of the bathymetry, and then he uses a magnetic map, something called magnetic anomaly map. And then he fuses it together and can combine it also with taking bearings to different landmarks and supporting it with the ship navigation system. So by measuring the magnetic intensity and the bathymetry, and then using some mathematics based on Bayesian mathematics called particle filters, then he can get some quite good positioning. And this is technique that actually could work even when you don't have good visibility and so on. So it's a smart technique where you take different data with low resolution to increase your own positioning. And the last example comes from another program called SMARC, Swedish Maritime Robotics Center. This is an underwater robotics research program ongoing, and it's hosted by KTH, Royal Institute of Technology in Stockholm. And the partners you can see on the lower right, Stockholm University and Gothenburg University are involved as well. And then we have FMV and FY, those are defense authorities. And then we have the industries like Saab and MMT, which is an offshore survey for company from Gothenburg. And in this program, the main research areas are autonomy, endurance, perception, and communication. And also here we have demonstrators. You can see them on the right. We are building some of them ourselves, and then we also have access to the big underwater vehicle that is located at Gothenburg University. And this is one example of the research ongoing, and it's using something called SLAM. And SLAM means simultaneous localization and mapping. And this is a really, really hot topic in all robotics, not only underwater. You find it with cars, indoors, air, everywhere. Everyone is working with SLAM. And SLAM means that you make your own map. You go around, you don't really know where you are, but you're creating your own map. And in this case, we use a multi-beam echo sounder to make a map of the seafloor. And then we try to estimate our position. And of course, now we are underwater, so we can't use the GPS, so we have to use other sensors. And then you can use this map when you come back, so to say, and estimate where you are. So if we would have a surface ship making this map, we could have used this map when we do the underwater navigation. So this is a kind of bottom correlation navigation. And the reason we are doing this in this program is that we are working with technologies to do long-range missions in unknown waters. For instance, going under the shelf or ices in the Arctic. And there you definitely don't have any maps, and nobody have ever been there in those areas. And connected to this, I want just to pitch another big global project ongoing. It's called Seabed 2030. It's sponsored by the Nippon Foundation and GEBCO, the General Bathymetric Chart of the Oceans organization. And this is a program that has the intention to map 100% of the ocean floor by 2030. And if they would succeed and we would have a good map of the seafloor, then navigation at sea would be much easier without using GPS, for instance. So, some conclusions. GPS is fantastic, but it's a very sensitive technology. And of course, you all have a GPS in your mobile phone, and most of those GPSs, they not only use GPS, they also use other kind of satellite navigation system. But it's sensitive, so we need new technologies to get a robust all-weather navigation system on the surface and under the surface. And it's very much based on sensor fusion of many types of sensors. And you see some example on the right, which you could use: bathymetry, inertial navigation system, magnetics, celestial objects could also be used in an automated way, and so on. And this development is very much driven by sensor technology, digitalization, autonomous system, mathematics, and AI. But finally, we don't have good enough maps of the ocean bottom yet. And that, I think, is a really big challenge that we should all strive for. And I saw a comment in the comment field before that in Sweden, the high resolution bottom map is actually classified data in Sweden. We are prohibited by the defense to make these maps without an authorization. And that is actually the case in some other countries as well. So that makes it more difficult to make this big map of the ocean bottom. Thank you. That's all.
Thank you very much, Roger. You brought the question away because it was there asking about the restrictions to map the seabed in Sweden.
Yes.
But I thank you very much, and I hand over to Christian again.
Yep. So then we'll go further with the next presenter, Cooper. Are you available online?
Yes, I am.
There you are. Okay. So the floor is yours.
Okay, thank you. Let's try and share the presentation. Okay. So I'm Cooper Van Franken, one of the founders of Bering Data Collective, and coming to you from Copenhagen, Denmark. And so Bering Data Collective is built around the concept of fishing for data. Fishing nets are an ideal platform for sensors to observe the ocean as the nets go down to the sea bottom, fish, and then come back up to the surface. In short, fishing vessels can catch data profiles of the water column while they're catching fish. Data can then be sent to users in near real time as the sensors surface along with the fishing gear. And the presentation today is focused on the subsurface data, as this is particularly difficult to collect from other platforms, and fishing activities are uniquely well suited to collect this type of data. So a quick example of data collected from a trawler very close to where we're focused today in the Kattegat. And you can see these temperature and salinity profiles. And just a regional focus thing, you can see a very strong salinity gradient on that bottom chart. Salinity inflows from the North Sea are particularly important for this region and for the Baltic, both for physical as well as biological reasons. Now, to understand why this approach can be so impactful to the broader ocean observation community, we need to talk about ocean observation today. And subsurface ocean observation today is really dominated by these Argo floats, which we've heard about earlier, especially from Fabien in his talk about the seals. And Argo floats are these autonomous profiling floats that go up and down in the water column on a 10-day cycle. And there's about 4,000 of them in the ocean at any given time. And if you look at this map here, it looks pretty good, you know, pretty even coverage. And so this color bar is showing the mean number of monthly measurements. So a lot of blue points, so roughly 1 measurement per month. And it looks like pretty good coverage over most of the ocean. But as we start to look in a little bit more carefully in shelf and coastal regions, you start to notice some holes. So this next set of maps, we're going to focus on where we are more concerned about today. And so this North Atlantic region and into the Baltic. And you can see that due to the operational limitations of Argo, there are holes in the subsurface ocean observations. And these data gaps are really pretty shocking, how little subsurface data there is in close to shore. You can see a few data points showing these red here. These are from buoys, but predominantly it's the blue lower coverage out in the deep open ocean. It's important to note that research vessel data is excluded from these analyses, but much research vessel data isn't transmitted in near real time to operational users. And it's not just that data is lacking from these regions, it's that it's especially important to have data in these regions because the conditions change more rapidly in the coastal and shelf regions than in the deep open ocean. And because these coastal and shelf regions are where the majority of maritime activity takes place, far beyond commercial fishing to other maritime industries, as well as recreational stakeholders. And this next map here shows the fishing activity coverage for the same time period. And so not only is there a lot higher intensity fishing activity in this area, but it's almost a perfect yin and yang pattern where the fishing activity takes place where the ocean observation today is lacking. And so this is an absolutely massive opportunity to contribute to filling these data gaps and complementing the observations from other platforms and working to improve the forecast and model accuracy where it matters most to stakeholders and ocean users. And so there's, of course, a very wide range of commercial fishing practices regionally and depending on economics. And so we're working with a wide range of fishing types and in a wide range of areas. So this middle picture is taken from a large factory trawler in Alaska. And then the other picture showing an indigenous subsistence fisher, Northwest Greenland. And it's not that one of these data collection opportunities is better than the other, but that each of these presents a unique data collection opportunity. And so larger vessels often cover a wider area and go into deeper waters. However, smaller vessels operate in a more consistent area and can therefore collect more consistent spatially and temporally, which can often be better for data time series. And so just kind of hearkening back to Fabien's presentation earlier, both of these pictures are shown in marginal sea ice, so marginal seasonal sea ice. And that's an extremely difficult data collection niche for automated data collection technologies, but something that both fishing vessels and seals gravitate towards because this is where a lot of fish hang out, and also that these platforms navigate the hazards of sea ice. So this is quite a good fit for both these opportunistic data collection approaches. And there's two important fishing gear types, two broad classifications here and how that relates to the data collection possibilities. And so mobile gear and fixed gear. Mobile gear, such as trawlers, is moved through the water column to catch fish. So it's lowered down, fishes, and then comes back up. And so this creates a profile where the GPS track changes over time, making this analogous to the data collection collected by a glider or something like that. And the second classification is fixed gear, such as pots or a gear like that. So the gear is lowered down. It sits on the bottom for hours to days, hopefully collecting fish, and then is hauled back up. So this is more analogous to a traditional CTD cast with added bottom time. And so another key piece to this puzzle is the sensors. And there's been a lot of development in this field in recent years, which is really making this quite a bit easier for all of us. And so they have to be compact and robust so that they can stand up to the rigors of fishing, but also not interfere with the existing fishing operations. And the other key piece is to have automatic wireless connectivity, so kind of this IoT capability so that data can be sent to a collection point on the boat autonomously. And so an example of data collected right here, you can see the sample page from EmonNet Physics. So I'm not sure if this presentation is available after, but there's a link there. Go check that out. And again, this is in the Øresund, so quite close to us here in between Copenhagen and Helsingborg. And this data is running in real time. Actually, this morning, there's some CTD data that came in and quite some interesting salinity changes over the last couple days that we were surprised about, an 8 PSU jump in salinity. And so what we're doing at BDC, in addition to outfitting data collection on boats, is working on a centralized data flow and built around the FAIR data standard. So findable, accessible, interoperable, and reusable. And so what we're doing is aggregating not just our own vessels, but other programs, more on that on the next slide, and pulling them into our centralized data hub with quality control, metadata standards, so making this data interoperable for the many different users. And then we distribute it either directly onto data users via ERDAP or indirectly using data hubs such as EmonNet Physics or Copernicus Marine, anything like that. And doing this, data providers increase their visibility and the impact of their data while having traceability and credit back to them as the original data producers, but balancing the needs of industry and the necessary confidentiality. So meeting the needs of industry while not compromising the scientific integrity of this data source. And really a key piece to this is the right data and metadata standards. So maximizing the reusability and interoperability with the wide range of data standards necessary to increase the usage beyond physical oceanography to fishery science and all the other ways in which these data streams can be used. And so, as mentioned before, it's not just us. And so this centralized data system is really a way to bring together this community, as we found more and more programs populating these little dots on this map, and both scientific and fishing industry-led programs. And so we're bringing this community together, and this really started as it was necessary for us to bring this data to the oceanographic community and necessary for us as a community to scale. And so the orange dots, scientific-led programs, green dots, industry-led initiatives, blue dots are our own data collection, and then pink dots are either science or industry who are interested in participating in the future. And it's important to note from the green dots that there are many fishing fleets who are collecting this data for their own purposes. So the fishing industry is up for it, and for a wide range of purposes, both transitioning to a data-driven business model, as well as having a vested interest in contributing to both fishery science and oceanography. And so now I'm beginning to conclude my talk. And so we've been discussing the subsurface data collection as this first illustration showed. However, the data collection opportunities on fishing vessels aren't just limited to subsurface. There's a wide range of data collection opportunities that can be collected both by adding new sensors to fishing vessels, as well as using already existing sensors on fishing vessels to collect not only essential ocean variables, but essential climate variables with sea surface data, as well as atmospheric data and weather data. And these data streams are not valuable just because, oh, it's more data. It's really, really important because all being collected on the same platform, these are co-located data streams. Co-located data streams are far more valuable than the sum of their individual parts, since they enable directly linking what's happening beneath the surface of the water in the water column to the surface of the water and then into the atmosphere. And these co-located data streams are really key for the future of coupled ocean atmosphere models, as well as coupled biological and physical models. And the ability to collect so many co-located data streams is really unparalleled in other autonomous or opportunistic data collection platforms. And therefore, there's a tremendous untapped data potential from the thousands upon thousands of fishing vessels that are operating in our oceans every single day. And so myself, the rest of our small team, we've been around just about 2 years, and it's really started to get exciting just in the last few months. Things are really, really picking up, but we wouldn't be here without many, many advisors. So thanks to everyone. And that's all I've got. So feel free to reach out either now or send me an email, any questions about that. Yeah, so thanks so much.
Thank you. And I would find it very interesting to see if we can. I will post the first question here while I wait for your comments online for us to post on all our 3 talkers this session. But I'm trying to combine a thought here to Amanda and Cooper, not so much Roger, I think, but he'll be the judge of that. Have you in any way tried to connect the data collection by crowdsourcing from the data collected by the individual fish with the data collected from the fishing vessels in trying to transmit a larger amount of data from 2 different sources? Have you tried in combining these? And let's see who will answer first of Cooper and Amanda.
I'm happy to take this one. So yes, very good question, because there's a huge opportunity here, and this is really the kind of key ingredients of ecosystem-based fisheries management, as well as starting to work on things such as like precision fishing technologies and data products like that. The catch data is a little bit more sensitive than the hydrographic data. That's one of the reasons that we started with this data stream, is that the fishing industry isn't very protective of this data stream. But we have been doing a little bit merging these data streams, and we're certainly exploring this, as well as talking with other data providers such as electronic monitoring, kind of automated catch data recording for future projects and proposals.
And if I could just add maybe a comment on that. Yeah, I think it would be really interesting to look at the actual knowledge of the people deploying these sensors and people working on the vessels. And I think that's where you could see a connection between crowdsourcing and collecting data through the sensors. And this way you would have sort of the perfect socio-technical network, so to speak, kind of a term that we use, where you combine social data, experiences, knowledge, with data that's actually being collected underwater in this case.
However, looking at the fishermen, they already today share data rather on bottom topography and so on than the catches. But I think that if you would add the IAS information as well, it wouldn't be very hard to find out where they get their catches. So, I mean, merging data from different sources would actually be very, very interesting. Not just, how should I say, in crowd foundation, also by open sources available on the internet, for instance.
I would like to comment that connected to this map of the bottom that we don't have. To get that map, we really need to use all sources we have, including different kind of crowdsourcing, even if it's illegal in Swedish waters. Today, if you buy an advanced depth sounder, it can be connected and send the data to a database and so on. So I would say there are a lot of collection, and one of the thing is bringing all this data together. And that is actually one of the purposes of this project that I mentioned, the Seabed 2030 project. The first thing they try to do is not to go out and measure themselves, that is actually to collect the data that already exists. And particularly if you look at the offshore industry, they own a lot of bathymetry data today. And some share it and some are more reluctant to share it.
Okay, if there are no more questions, then we should try to move on and say thank you for our 3 presenters during this session. Very interesting, from very diverse input areas, but sharing along how to collect data for the oceans. So now we'll try to see if we can connect to Torsten out in the laboratory outside here.
Hello, hello. Now we are in the electronics workshop where we're going to wrap up this block number 2. How can we collect data? And we're doing that by talking with a group of people who feel very passionately about collecting data from the ocean and have some different perspective about how that can be done. And we're starting with you, Olle. You are oceanographic technician at Voto. And Voto, that is Voice of the Ocean. Tell us in 2 sentences what is Voice of the Ocean, Voto?
So Voice of the Ocean is a foundation that is a non-profit foundation that has decided to collect data around and try to get more data from the Baltic to provide to researchers to use, and we kind of provide the data and the tools for future researchers to use, basically.
All right, wonderful. Then I will ask first you this question. Around us we see robotics equipment. Why do you use ocean robots for collecting data?
So I think the robotics or like autonomous vehicles are very interesting because of it kind of bridges an area between remote sensing and vessels, where you can get like really high resolution data from these vehicles and still have the endurance that you normally cannot have with a vessel that has a crew and so on. And you can also build a fleet of these tools, so you can you can scale the operations quite big.
You mentioned endurance.
Mm-hmm.
What kind of endurance are we talking about?
So, for example, this platform here, and it's the same as that one. It can basically be deployed all year around, collecting data and transmitting it back to shore. It's propelled by wind, and the only time it needs maintenance is when you need to remove biofouling and take it in for repairs. But other than that, it should be self-going.
All right. Okay, that's amazing. Okay, you are sort of a new player, Voto, in collecting ocean data from the Baltic Sea. Will you make a difference?
Of course, we will make a difference.
All right.
I think bringing these tools into the Baltic and our waters is something that will really enhance the quality and resolution of the data that exists. And I think this is the future.
This is the future. I think you are right, Olle. Thank you very much.
Thank you.
Next, we are going to meet Ola Benderius from Chalmers University of Technology here in Gothenburg. You work at the so-called Revere Lab. And your first focus was not at all ocean robotics, but rather something else.
Yes, we started with on-road autonomous vehicles in 2015 at Chalmers Laboratory Revere. And we started then with trucks and cars, as everyone else did. But now recently then we have moved over now to actually marine applications as well, which is very exciting now.
Okay. And we are going to see a little bit of your what you have done in a while. The platform CCAT is something you've been working on. Was it a difficult transition going from cars and trucks to maritime platforms?
Actually not. I would say that, I mean, in automotive, there have been a technological push for a very long time. And also the new startup companies have done a lot in recent years with the AI technology and also sensors and so on. So we felt that it was a very natural step then to basically bring this into the marine environment, where we have a more, I would say, chaotic environment. It's also more free. We can do more things. Traffic environments are quite restricted, which is a little bit boring in one sense. So the marine environments are really interesting to us to experiment and to try new things, new algorithms and new AI stuff. So I think this is not hard, but more exciting.
All right, and you are not you're not scared off when you hear Olle talk about endurance for months of these platforms?
No, I mean this is the same for the automotive industry. Of course, we need to build robust systems. So that is also something that we have invested a lot of resources in our lab. So we have a lot of research groups working with that, especially then on the system level. So we have basically built from bottom up, really the system from scratch. We have our own software, OpenDLV, in the lab that runs all our systems, both on land and water. So endurance is something that we do, definitely.
Okay, thanks a lot, Ola.
Thank you.
Please. Next comes a very special guest from the Science Club in municipality of Lysekil. You are a student in the Science Club, Elsa.
Yes.
Why did you join the Science Club in Lysekil?
I think it's very fun and interesting to work with science. And now we're doing this Drifter project. And it's amazing because we can help to develop this amazing scientific instrument, which can actually help real research. And it's amazing that we can do this while still being students.
It is indeed amazing, and for those of you who has followed the chat and the posts on Instagram, you know that Elsa and your friends in the Science Club, you deployed this morning the Drifter that the Science Club has built, and you retrieve data. Have you had the time yet to look at the data at all?
Just a short bit. But we looked this morning, and it worked really well.
Okay. So once you have feel familiar and confident using a Drifter, perhaps the simplest form of an autonomous ocean data sampler, would you like to move on to other types of robotics?
I think that would be really fun, but we'll see in the future.
Yes, of course. Great to have you with us, Elsa, and we will see more from the... Please. We will see a little bit more from the Science Club later during the afternoon when they show and tell us about their Drifter. Daniel, please come up here.
Okay.
Okay, you represent the Swedish Meteorological and Hydrological Institute, the Swedish Met Office, so to speak. Very much operational marine environmental monitoring. What do you think when you see the robotics equipment around you? Is this something for SMHI?
Yeah, I think this is the future for monitoring. Beside continuing with some traditional data collection methods,
Which are mainly?
it's water sampling, measuring profiles with instrumentation called CTDs and
Mounted on crewed vessels.
yeah, exactly. So it's work intensive, but it's reliable. So yeah.
But when we hear Olle and other people here talking and describing it, it seems to me that this is relatively mature technology. Why is this? Are there other challenges except for endurance, which seems to be already good?
Yeah, I think the technology is on a good way, and I think maybe we're not up to date with the latest as well. So maybe we can be convinced in a near future. But it's so high level of readiness, reliability. Also, autonomy is important. Even more important, I think, for them to have working with long-term monitoring, because you need to reduce the workload for piloting and stuff. So if you can develop or improve even more the autonomy with AI modules that aid the pilot and really reduce the workload, I think it's manageable very soon. Then we have the next challenge to convince our organization and also the government and that we can starting to implement this in the monitoring program, which takes a lot of work and money as well. So it's more like a political question.
Okay, there are
and it's slow. What do you call it? A big ship.
It's not easy to turn a big ship like SMHI and even
not
the larger
SMHI,
programs.
Even more so the ones ordering the data from us. Yeah.
Okay.
Okay.
Nice talking to you, Daniel.
Yeah.
And last one up is Professor Anna Wollin from University of Gothenburg. You're professor in physical oceanography. And you are the project leader for Scoot's flag robot. That's my way of putting it. The AUV RAN. Please tell us a few sentences about RAN.
RAN is an 8-meter long robot that has a capacity to go out on missions up to 36 hours, which converts to 300 kilometers roughly. And because she is large, she has capacity to have big sensors on her. And I think maybe that is the most important difference between the smaller robots. So RAN can have quite sophisticated acoustic sensors, and she has a CTD that is of the same scientific quality as the stuff that you carry on board research vessels. And we use her mainly to go to do studies in Antarctica, to one of the most remote and inaccessible oceans on Earth, I think. That is the oceans underneath the floating glaciers in Antarctica. So that's water covered by several hundreds of meter thick ice. And the only way to get data from there is by sending in an autonomous vehicle. And you can't only send it in, you also need to know exactly where it is every second. And that's also one thing that RAN does well, navigation underwater and keeping track of its position.
All right. And once you have sent RAN under the ice around Antarctica, several hundred meters of ice, did you say that?
Yeah.
Impressive. Can you follow her progress, or does she navigate completely on her own?
She navigates completely on her own. So it's quite nervous waiting on board for her. So we send her out on 36-hour mission, and then we go nail biting for 36 hours, and then she hopefully comes back.
All right. So that's a piece of equipment. Actually, we were hoping that we would have Ron on display today, and we would have just walked through the door that is behind the camera right now and taken a look at her. But she is now not in Gothenburg. She is
New Zealand at the moment. So it's a big European project where she's used in a. So they will look at earthquake damage on the New Zealand seafloor with her. Very exciting.
right. Just to get it right here, there are always trade-offs when it comes to technology. We have seen these robots around us, fairly small, not a 7 meters long thing. They can take not as many sensors as Ron, but they seem to have a lot longer endurance. But that is the trade-off you need when you want to go under several hundred meters of ice.
Yeah, that's absolutely right. You can't have it. There's no way to build a machine that's long term and has the navigational capacity and can be equipped with this.
Yeah. So propulsion of Ron is by means of
Propeller and electric batteries.
right. So
Yeah.
it's the lifetime of the or the endurance of the battery pack that is the time limit.
That's right.
Okay.
Yeah. And you need quite a lot of power because she needs to have a steady speed in the water in order to have good navigation and get good data. So that is the trade-off. I wish we could have many Rons to send out for months. That would be fantastic, but not yet, unfortunately.
How many Rons are there around the world of her capacity approximately?
About 40, I think, around the world. But we were the first ones to get one for academic purpose. Most of them are used for military and oil industry, energy industry.
All right, and I guess that they are not so happy to share the data they collect for the military or?
The military is not, no, but the energy sector, they can share some
All
of
right.
their data, I think.
Okay. Fantastic. I think that ends, thank you very much, Anna. That ends this block, and we are going to a break, I think. Isn't that right?